Hello, my name is Anastasiya Salova and I'm a graduate student at the University of California, Davis. Today I will talk about my work on cluster synchronization and hypergraphs, which I did together with my advisor Raisa D'Souza. First, let me introduce cluster synchronization and networks with dyadic interactions. In this case, the network structure is encoded in the adjacency matrix A, and the state of the node evolves according to its self-evolution function f and the coupling terms in which the function g describes the interaction between the node and its neighbors. In such systems, a fully synchronized state is admissible, but so are some of the more intricate patterns of synchronization, in which oscillators can be divided into fully synchronized clusters, but each cluster follows a distinct trajectory. An example of such division is shown here, where different clusters are represented by different colors. A partition into fully synchronized clusters is admissible if the effective interactions between any node in one cluster and any node in a different cluster are the same, no matter which nodes are chosen in each cluster. For instance, here each yellow node gets input from two black nodes, one purple node, and one teal node. The interactions within each synchronized cluster can be ignored. For instance, we can ignore the edge between those purple nodes because the interaction between the purple nodes goes to zero if they're fully synchronized. The effective interactions between different clusters can be represented by the quotient network as shown in this figure. The effective dynamics of each cluster is contained in the system of ordinary differential equations, and these ordinary differential equations define the synchronization manifold of this cluster synchronization state. This coupling scheme admits full synchronization as well as several cluster synchronization patterns. Here I show examples of 2, 4, and 8 cluster patterns. Each cluster synchronization pattern can be encoded in the cluster indicator matrices E, where each indicator matrix has diagonal elements of 1 if the nodes belongs to a cluster K, or 0 if it does not. Similarly to networks with dyadic interactions, the hypergraphs could also be partitioned into clusters in a similar manner. In this case, we have to define the interactions between the clusters not only in terms of the quotient network, but also in terms of the quotient hypergraph. For instance, dyadic edges with two black nodes contribute to a yellow node, and dyadic edges with purple and teal node also contribute to each yellow node, which helps us characterize the state of the yellow node. Checking whether a cluster synchronization pattern is admissible for a hypergraph is easy. However, finding admissible cluster synchronization patterns efficiently can be a non-trivial task. To find some of the admissible cluster synchronization patterns, we can project a hypergraph onto a network with different kinds of edges corresponding to different orders of interaction. For instance, gray here corresponds to dyadic interactions, and green edges correspond to triadic interactions. If the coupling function does not depend on the state of the node itself, the admissible cluster synchronization patterns of the hypergraph exactly match those of the projected networks, and vice versa. This can be useful since the algorithms that partition networks into nodes that can be synchronized already exist. However, the situation can get more complicated if the hypergraph coupling is non-invasive, directed, or Laplacian. Finally, I will discuss the stability of cluster synchronization patterns, as it determines whether those patterns can be observed in experiments or natural systems. The stability of the system is encoded in this variational equation, where we can sum over all the possible synchronization patterns on individual hyperedges, and the same pattern corresponds to equal elements in the full Jacobian. The projected Laplacian matrix L encodes the interactions on the hyperedges with the same pattern of synchronization. It can be calculated using the adjacency matrix projections. In turn, those projections can be obtained by selecting rows and columns of incidence matrices. Specifically, we select rows and columns that correspond to the state of the receiving node in a given pattern, the state of the node that we take the derivative with respect to in a pattern, and the edges that correspond to the other states in the pattern. In principle, this is enough to do stability calculations. However, some of the natural and engineered systems are very high dimensional, so we're interested in dimensionality reduction that can be done to make the calculations more tractable. For systems with dyadic interactions, this dimensionality reduction can be accomplished by block diagonalizing the full Jacobian using the simultaneous block diagonalization of the dyadic Laplacian together with the cluster indicator matrices. To block diagonalize the Jacobian arising from higher order interactions, we need to simultaneously block diagonalize additional matrices highlighted in violet here. These matrices come from the projections of the Laplacian matrix on a particular cluster synchronization pattern. We consider two patterns of synchronization to illustrate this example. For each pattern of synchronization, we provide a set of matrices that need to be block diagonalized and the resulting block Jacobian structure. In this case, we can see that the Jacobian block diagonalization is finer for the case of two clusters. To summarize, in this talk I have shown how patterns of cluster synchronization and hypergraphs can be deduced from their structure. More specifically, hypergraph equitable partitions can lead to cluster synchronization patterns in systems with adjacency coupling. Can also show that similar sets of restrictions can be posed on systems with different types of coupling, such as Laplacian or non-invasive coupling. For high-dimensional systems, we can simplify the stability calculations by block diagonalizing the coupling matrices. To do that, we need the Laplacian matrix. The Laplacian matrix is projected on different patterns of synchronization, as well as the indicator matrices for different clusters in the system. As a next step, we want to study more concrete examples of higher order interactions, and we want to illuminate how these interactions can stabilize or destabilize the synchronization patterns in systems with different topologies. Finally, I want to mention that I'm planning to graduate this academic year, and I'm interested in all the postdoctoral opportunities that may be available and relevant. Thank you.